Hi everyone. Before I start with section 2.1 today, I want to remind you that the written assignment is now on Brightspace. So please go to the assignment section on Brightspace. You'll be able to see the assignment there. Just download it, do the questions, and upload it back again on Brightspace. It's going to be due June 4th, so make sure to submit it on time. If you have any questions or if you need any hints, just email me. I can either email you some hints or we can do office hours and I'll explain the ideas of the questions for you if needed. Okay, so let's start with section 2.1, which is areas between curves. So in chapter 1, we talked about finding the areas under a certain curve using the definite integral, whether it was evaluating the definite integral directly using the antiderivative or using some geometric formulas, or even using Riemann sum to approximate the area. It was only under one curve. So in chapter 2 here, we're going to start talking about finding areas between any curves, whether it was one curve, two curves, or many more. Okay, so here we have three main goals today. First, I'm going to find the areas between two curves, but with respect to variable x, which is my independent variable. Then I'm going to find the area of a compound region. Then I'm going to find the same area between two curves, but with integration with respect to y, which is my dependent variable. So let's start with the first theorem for today. Let's assume that I have two functions, f and g, that are continuous, and I have f is bigger than g over a certain interval ab, and let me denote R to be the region bounded above by f, below by g, and left and right we have lines x equals a, x equals b. Then we can find the area of the region A to be the integral from a to b, f minus g. So let's look at the graph to understand it more. So I have my function f, and I have my function g. F is bigger than g here on the interval from a to b. The reason why f is bigger than g is because if you look at the graph, f is always above the curve of g. Now R is the area, is the region bounded between f above it, g below it, line x equals a from the left, line x equals b from the right, and that's my region R. Now I want to find the area of this R. So apparently this area could be evaluated using a definite integral by integrating from a to b, then upper function minus lower function always. So that's why you have this area here, upper minus lower function. So let's look at it in terms of rectangles. Oops. Sorry. So if we do the rectangles criteria like we did in the first chapter, if you sum all of the areas of all of these rectangles using a Riemann sum, then you take the limit of that Riemann sum, that would be your area. So let's look at one of the rectangles here. If you look at this rectangle, the above point here is going to be your f of xi star. And the below point here, obviously it's going to be g of xi star, right? Because this is the curve of g and that's the curve of f. And we know that the width of any rectangle, it's always given by delta x. Now the area of each rectangle is always width times height. Now the width we know, it's delta x. Now to find the height, if you subtract f of xi minus g of xi, that would be your height. So that's why when you do the Riemann sum, you're going to have the height, which is f minus g, multiplied by the width, which is delta x. Now when we did Riemann sum with only one function, we had f of x inside of the integral. But since I have f minus g for each point, the function that we're going to have inside of the definite integral is just f minus g. Okay, it seems complicated, but it's really not. It's just taking the area for a certain region where you integrate on a certain interval, and it's always above minus below the function. So let's do an example here. If I want to find the area of the region R, where R is bounded above by f equals x plus 2, and bounded below by g equals x squared, on the interval from 0 to 1. So the first step, obviously, is I want to graph it. So if we graph x plus 2, it's going to look something like this. And obviously, if I graph g, x squared is just kind of like this. And now we want to identify where is the region R. Because the area between these two curves is all of this, right? But since I only have the interval from 0 to 2, it's only from 0 to 2 here. Now let's make sure that the 2 is in fact the point of intersection here, because it could easily be here. To do that, you always find the points of intersection by equaling the two functions. If you factor it, so 2 is in fact this point of intersection. So perfect. Now I have this area to be my region R. So if I want to find the area of R, you integrate on the interval from 0 to 2, and then f minus g, upper minus lower. So my upper function here is the blue line. So that's x plus 2. Then minus, always, you subtract the lower function here, which is the purple graph, which is x squared. And now you integrate easily using the antiderivatives. So this is x squared over 2 plus 2x minus x cubed over 3 from 0 to 2. Upper bound minus lower bound. That would be 2 plus 4 minus 8 over 3 minus 0. Okay, so let's try a different example. If we look at problem 2 here from the book, I want to find the area of the bounded region between f and g, where f is the function x squared and g is 3x plus 4. And I want to find the area of this region here. So to find the area, I want to identify first the points of intersection, so I'll know which are my A and which is my B. So to find the points of intersection, you just equal the functions and solve it. So I know that g is 3x plus 4, and that should be equal to x squared. To solve it, take everything to one side. And just solve normally. So I have x to be 4 and negative 1. So these would be my bounds for the integral, because here, this is the start of the region R, and here, it's the end of the region R. So sometimes you can easily identify them from the graph. So if you can easily find the bounds from the graph, you don't need to find the points of intersection. So now the area would be just the integral from negative 1 to 4, then upper function, which is my g, minus lower function, which is my f. So that would be 3x plus 4 minus x squared, and you integrate normally. So that would be just 3x squared over 2 plus 4x minus x cubed over 3 from negative 1 up to 4. Now you plug in upper bound minus lower bound and that would be your answer. So you can simplify it and find the answer in the simplest form. Okay, so this is quite easy, right? Because whenever you have a graph so far, you can easily identify the upper and the lower graph because they only intersect at one region. So now what happens if my functions intersects and give me different regions? So here the area of compound regions comes. So if we have regions bounded by the graphs of function that cross one another, so if they cross, causing different parts of regions, we need to modify this process by applying an absolute value for f minus g. So it's the same exact thing, but now we have an absolute value. So again, if I have f and g to be continuous on a certain interval a, b, but here we don't have restriction where f is bigger than g over the whole interval. And similarly, we have r to be bounded by the graphs f and g and the lines AB. The region is the same exact thing, but I need to take an absolute value. So the reason why we take an absolute value is because in these types of questions, you'll have a part of the region where f is bigger than g, but the other part of the region, g is bigger than f. So here you need to identify an absolute value to express that difference. We'll understand it more once we do an example. So here, technically we're breaking up the interval AB and we're evaluating several integrals for each part of the region, depending whether f or g is bigger in each region. So let's start with this example. If I have f to be x, g to be x cubed, and I have an interval from -1 to 1, and I want to find the area of R. So easy. Let's start by graphing, right? So the line x, this is my line f equals x, and then I have x cubed that looks something like this. And now let's see, like the first step is always finding the points of intersection. Finding points of intersections means I want to equal the functions and solve an equation. So now x cubed is equal to x. If you take x to the other side, x as a common factor, I'll have 3 points of intersection, which makes sense because if you look at the graph, you have 3 points of intersection here. So that's -1, 1, and here is the 0. Now, since we want to find the area on the whole interval, -1 and 1, if you can see, I have 2 areas between my graphs, which means I'm going to have 2 areas, so I need 2 integrals. Okay, now let's see. Since I have 2 integrals and 2 areas, and my functions cross on multiple points, I want to find the area, but I have an absolute value. So when you have an absolute value, you want to see whether your function is positive or negative inside of that absolute value. So let's look at the first interval that we have. So from -1 up to 0, if x is from -1 up to 0, if you can see, the purple curve is above the blue curve, which means that on this interval, g is bigger than f of x. So if I'm taking the absolute value of x minus g, since g is bigger, this is going to be g of x minus f of x. And if you look at the second part of the interval we're integrating over from 0 to 1, you'll notice that the blue curve is above the purple curve, which means that f of x is bigger than g of x, which means that the absolute value of f minus g of x is just f of x minus g of x. Because we always want to find, like, when you take an absolute value, you always want to get something positive. So here, since I'm subtracting bigger minus smaller, you're going to get something positive. And similarly here, since g is bigger than f, so bigger minus something small, you're going to get something positive, which agrees with the definition of an absolute value. So now, to write it as an integral, if I want to integrate from -1 to 1, the absolute value of my function x minus x cubed dx, I can easily divide it to two intervals, from -1 to 0. And then we said that from -1 to 0, the absolute value is just g minus f. So that would be x cubed minus x dx plus the second integral from 0 to 1. But from 0 to 1, the absolute value is just f minus g. So that would be just x minus x cubed dx. And we integrate normally. So that's x to the 4th over 4 minus x squared over 2 from -1 to 0, plus x squared over 2 minus x to the 4th over 4 from 0 to 1. You do upper minus lower, and you find the value. Okay, so sometimes the graph is already there. Whoops. Oh my god. Okay. So if the graph was already there, it makes life much easier, right? I don't need to graph. So here, if you can tell, I have area 1 and area 2. On area 1, f is bigger than g. But on the second area, g is bigger than f. So when you have that case, you know that the total area, we need to take an absolute value. So first of all, points of intersection. Here, I can obviously solve it like, oh, cosine is equal to 1/2, do the equation, solve it, and find the values of theta. Or here, it's obvious. The point of intersection here is just 1. So this is the point where I'm going to split my integral. And since when we're integrating from 0 to pi, I'm going to have the total area is from 0 to pi. So the reason why I know it's from 0 to pi, because they asked to find the area over this interval. So that's why I'm integrating from 0 to pi. And if you can tell here, pi is 3 point something. So we stopped here, so it has to be pi. Okay, so back again, I'm going to find the area by taking the absolute value. Then we're going to split the integral at point 1, because this is the point where the switch happened, where f was bigger than g, then here g became bigger than f. So I need to split it to do upper minus lower. So here, since I have the graph, you can easily do like, oh, on this part from 0 to 1, my upper function is f, so that's cosine theta, minus my lower function is g, so that's just 0.5. So by practice, it will come naturally, or like which function you want to choose. You don't have to do like the definition of an absolute value all the time. If it's obvious from the graph, you can just use the functions from there. So here it's obvious, since upper minus lower is just cosine minus 1/2. That would be my first integral, plus I'm integrating from 1 to pi, upper minus lower, so that's 0.5 minus cosine of theta d of theta. And we integrate easily. So cosine would be sine theta minus 0.5 theta from 0 to 1 plus 0.5 theta minus sine of theta from 1 to pi, upper minus lower, minus 0 and simplify. Okay, so let me recap so far what we've done. If you want to find the area between two curves where these curves only intersect at certain points, creating only one region, you find the integral by finding the points of intersection and then integrating from the beginning of the interval to the end of that interval, upper function minus lower function, and you integrate easily. The second thing, when we have a compound area, is where we have two, or even like you can have 3, 4, up to 5, or like infinite points of not points, like you'll have like different regions. So when you have different regions, you have to pay attention if the upper and lower functions switch. So for example, in this question, f and g switched at a point of intersection, so you have to split your integral into 2 parts or 3 parts, depending on how many regions you have. So when you have different regions, you only have to find the points of intersection where the region flips the above and below functions, kind of, and then you always do upper minus lower function. Okay, now the next thing that we're going to talk about is integrating functions and finding areas, but with respect to y, which is my dependent variable, because it depends on x to find the values of y. So here, why this is useful, sometimes instead of dividing the region into 2 or 3 or whatever parts, we can evaluate it with only one integral if we're integrating in terms of y. So let's look at the graph here and see why this makes sense. So here I have these two functions, y and v. If I take that region R to be this, and I want to find the area of it, instead of doing upper minus lower, I'll do right minus left function on the interval from C to D. So if I'm evaluating this area, it only uses one integral. But let me show you, if we're taking this function in terms of x, so here I have a point of intersection, which means I have to divide my area, because here my upper function is the line D, but my lower function is the function V. And on this region here, my upper function is my line D, but my lower function is the function U. So here we have to use two integrals. So to avoid that, I'll just integrate in terms of y and use right minus left, because this whole region, this function is always to the right and this function is always to the left. So that's why it works. Now let's look at it when we're doing rectangles. If I have a rectangle, here my height would be my delta y. So delta y is the width, but using the y values. And my, this is my height, the height, yeah. And my width here is going to be u of y minus v of y, because these are my values of u's once you plug in y's in them, and this is the value of v once you plug in y in them. So my height would be delta y, and my width would be obviously the difference between u of y minus v of y. Now if we're doing a Riemann sum, I'm going to find the area for each rectangle separately, which is u of y minus v of y multiplied by delta y. So that's the area for each rectangle separately. But if I want to find the area of this total area, I need to sum all of these areas. So it's going to be the sum of this, and if you take the limit, you get the total area of the area between these two curves, which is just the integral from c to d u minus v du. It's going to make more sense once we do an example. I know it's a bit confusing so far. Okay, so let's read the theorem and then do an example. So if we have two functions, u and v, that are continuous, and these functions are in terms of y, which is my dependent variable. And similarly, I have u to be bigger than v on a certain interval. R is the region bounded by the function u from the right, the function v from the left, and the lines u equals d and u equals c. Then the total area would be the integral from c to d, u minus v. Right function minus left function. Okay, so let's try this example here. I want to find the area bounded by the square root of x and g of x equals to x on 0 to 1. But here I want to integrate it in terms of y. So let's start by graphing the functions. This is the square root of x. This is my line x, and we want to find the area between on the interval from 0 to 1. Let's find the points of intersection first and find u of y and v of y. So here, u of y should be my right function because this is the area, or this is the region that I want to find the area for. U of y is my right function, so that's just going to be y, because here this is the line y equals x. And v of y would be obviously the square root of x, but v of y is a function in terms of y. So to find it, I need to solve this equation here. So when you do square it, you get y squared is equal to x. So your v of y is just y squared. Now the points of intersection, y squared is equal to y. So y squared minus y is 0. So I have 1 and 0. So from 0, up to 1. So the area here, if I want to find it in respect to y, so my c is 0, my d is 1. So from 0 to 1, right minus left. So that would be y minus y squared d of y. So that's just y squared over 2 minus y cubed over 3 from 0 to 1. Upper minus lower, you're going to get this, which is 1, 6. Okay, so far this does not make sense. Like, why go through all of this trouble and evaluate something that we can easily find from upper minus lower in terms of x, and not like find the new values of the function in terms of y, find points of intersection of y, and so on. Let's try and do this example where I'm gonna find the area with respect to x first, and then the area with respect to y, and see why integrating in terms of y is much easier. Okay, so let's start. I have x to be 2 minus y, and x to be y squared, and I have y to be from 0 to 1. So since I want to evaluate first with respect to x, I want to find the functions in terms of x. So here, if you solve it, you're going to get y to be equal minus x, and then y to be plus minus the square root of x, right? But here, which one should I take? It all comes to the values of y, or like the domain of y that I'm taking here. So since y is in the interval from 0 to 1, y must be positive radical x, which is perfect, because now I can just graph these two functions easily. I know that the square root of x looks like this, and then 2 minus x looks like that. So let's find the points of intersection. If you square both sides, and you solve, you get x to be 4 and -1. That does not make sense. I think I made a mistake here. Wait, sorry. This has to be 4 minus 4x. Yeah. So now when you take it to the other side, you're going to have these 2 points. Yeah. So x is 4 and 1. So this point of intersection here is 1. And there's another point of intersection 4, but it's out of our domain, so I'm not going to take it. Okay, so now if you see, once I do that, I'm going to have 2 parts of the region, which means I'm going to separate my integral into 2. So here, if I want to find the area from 0, I think this is 2, yeah. I'm going to find it from 0 to 2. Because here, although y is from 0 to 1, my x is going to be from 0 to 2. Okay, so if I want to do that, I'm going to take the absolute value of f minus g of x, d of x, since I have 2 regions. And now on the first region, from 0 to 1, upper minus lower, that's the square root of x minus 0, d of x, because this line is y equals 0, plus the integral from 1 up to 2, upper minus lower, so that's my 2x, 2 minus x minus 0, d of x. And you can integrate easily. You're going to get x from 0 to 1 plus 2x from 1 to 2. If you simplify, you're going to get 7 over 6. Now using finding the area with respect to x created 2 regions, which created more work for us. But let's think about it with respect to y. So if you graph it, you're going to have 2 minus 1 looks like that. Y squared looks like this. So we're going to have this area here, which is the same exact area that we had on the first example. But here, my u of y is my right function, which is just 2 minus y. My left function, which is v of y, is just y squared. And we're integrating. Okay, let's find the point of intersection first. So we're going to have y to be 1 and -2. So -2 is this point here. I don't care about it because I'm only integrating from 0 to 1. That's the domain of y that we're taking. So the integral from 0 to 1, if you can see, it's always right minus left. There is no separation of the region. So I'm only integrating one integral from 0 to y, from 0 to 1, u minus v, which is 2 minus u, 2 minus y, minus y squared dy. If you integrate it, you're going to get 2y minus u squared, y squared over 2 minus y cubed over 3 from 0 to 1. Once you plug in upper minus lower, you're going to get 7 over 6, which is the same exact answer. So here, it's all about whether it's easier to integrate in terms of x or easier to integrate in terms of y, depending on the region that you have. So here, if you look at it with practice, you're going to see like, oh, this area here splits when I'm doing the values of x, so it must be easier to do it in terms of y, because here I only have one region, whether in terms of like right minus left functions. So it's all about practice. With practice, you'll have the ability to choose whether you want to integrate in terms of x or in terms of y. So yeah, just keep in mind, I'm integrating in terms of x, the area is always upper minus lower. If I'm integrating in terms of y, it's always right minus left, and you take the starting point and the end point of the region that you have, and these would be your bounds. Okay, so that's it for section 2.1. You have these suggested problems from the section for extra practice, and you can do problems from 1 to 5 from homework 2. Please, if you have any questions, just email me and I can explain further, or if you need office hours, let me know. Good luck, and I hope this week goes well for you.